Hello and welcome. I'm sorry about that. I wasn't aware that I had started recording. So in this final video for chapter 26, we go through some more visualization tools for the electric potential. And on Blackboard, you can find, I'm going to be posting some web links that can give us some more ways to visualize this concept. Because again, what we're doing is we're trying to visualize a scalar, a numerical value at every location in three-dimensional space. And so this next one we want to do is for a point charge. Okay, what we do, and this one is the building block for all other types of charges. And we started with the parallel plate capacitor, but really it's the point charge that's the building block. Even the PPC comes from this definition. So what's the potential, electric potential for the point charge? It looks similar at the bottom here. It looks similar to that of the electric field. But there's big differences. First difference is that it's only divided by R. It only depends on distance, not distance squared. And it's still a scalar, right? We're still dealing with the scalar. So where does this formula come from? Well, what's the definition of the electric potential? The definition of the potential created by a source charge is the electric potential energy it shares with the test charge divided by the magnitude of the test charge. So to get this formula, you have to know the force, starting with Coulomb's law, the electric force between 2 point charges. We find the electric potential energy between them, which we did in the first video for this chapter, and then we divide by this test charge. So that's how you get this formula. Okay, so that's going to start with, okay. And just like the electric field, the electric potential extends in all space, and it's going to be decreasing the further out you get. Okay, just like the electric field. So if you remember what the electric field looks like for a point charge, for a positive charge, the electric field vectors are all pointing outward, radially away from the positive point charge, and that's exactly the direction in which the electric potential is decreasing. So that's where we continue with this analogy. So what are some ways to visualize the electric potential of a point charge? Well, the first one is a graph. Okay? Since this potential is the same over all radial distances, since it has spherical symmetry, we can just draw the graph. And so this is a graph of y equals 1 over x, pretty much. I mean, we have to have units, we have to multiply by the charge. Okay, so that's how you that's the actual graph of the potential as a function of radial distance from that single point charge. But these spheres on the right-hand side are what are called equipotential surfaces, and those they look like Gaussian surfaces from chapter 24 actually, but their role is a little bit different. In fact, I think the spheres, the point charge is the only example where the Gaussian surfaces are the exact same as the equipotential surfaces. So what does that mean here? It means that the value of the electric potential is this exact same along every point on a sphere of constant radius, which is what you would expect because the formula for the potential doesn't change with angle, you know, along an x-axis or y-axis, z-axis, or a plane or whatever. So every constant radius, every sphere of a certain radius will have every point on that sphere will have the exact same value of the potential. What that means is that there's no work done, the potential energy doesn't change as another charge is moved from point to point on that thing, right? If this seems kind of strange, this is exactly what's happening in circular orbit and gravity, right? An object that's in circular orbit, right? It maintains a constant speed, so there's no work done. So it's actually traveling on a constant gravitational potential surface. I'm not going to, there is such thing as gravitational potential, but we won't get into those analogies in this class. Okay, those are two ways to visualize it. There's also the other two ways, right? The one is a contour graph where the circles are extending outward, and a lot of these graphs, these contour graphs, the contours are constant decreases. So it's like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and you can see how they get further spaced out. This final graph, this elevation graph of the potential of a point charge is really interesting because it definitely shows in dramatic fashion how the potential decreases for a point charge the further away you go, and it definitely rises nearly up to infinity, right? We never, you can get as large of a scale you like, but eventually, it's just up to numerical error. So those are 4 ways to visualize the electric potential of a point charge. What about a sphere? Because again, if you notice in chapter 23, we built up from the concept of a charged particle, electric field of a charged particle, we built up all these electric fields of different shapes. We're trying to do the same thing in this chapter where we build up the electric potentials from different shapes. And so a charged sphere, this gives you the formula for the electric potential on the surface of a charged sphere. If it were to go further out, right, the electric potential further away from the surface of the sphere looks exactly like that of a point charge. And in the center of inside the charged sphere, if it's a conductor or a spherical shell, the electric potential is actually not 0, it's actually constant. Yeah, it's actually constant because the entirety of the interior, again, if it's a conductor or a charged shell, the entirety of the interior is an equipotential. What about for more than one point charge, right? For more than one point charge, we can literally add the numbers together to find the potential of multiple point charges. So if we hop on here real quick, let's say if we were given like a positive charge and a negative charge and another positive charge right here, right? Okay, if we were given 3 charges and asked to find what's the potential at this location in empty space, we would have to do these 3, like R1 and then R2 and then R3. We'd have to calculate this number 3 different times, changing the values of the charge and changing the values of the distances, but we would just add the numbers together. In the case of the electric field, we have to do complicated vector components, and I know vector components aren't complicated, but they're still sometimes a chore, right? You still have to do it, and you still have to do the calculation. So this is how you can find the potential if there's more than one charge. In particular, that of a dipole, actually. The electric potential of a dipole is kind of important. And there's a couple ways to visualize this as well. We only do the last 2 visualizations for the electric potential of a dipole because the other ones aren't good. The other ones are a little bit kind of difficult to see. You can't do a simple graph of potential as a function of, say, some coordinate, because the potential changes from distance coordinate to coordinate, and so that doesn't work. And so you have a nice contour map here where the electric potential increases, or when it's near the positive charge, when it's near the positive charge, the electric potential decreases as it goes closer to the negative charge. So no matter where you're at on this graph, whatever equipotential surface you're on, you're always going to be, the closer you get to the negative, the potential is going to be decreasing. And this elevation graph is pretty interesting because you can see the fact that the charges, no matter where, if you have a dipole that's fixed in space, if you release a positive charge particle, no matter where you release it from, it's always going to be pushed away from the positive and eventually end up finding its way towards the negative. Unless it's released directly above the positive charge along the axis of the dipole, it'll just shoot off to infinity. But everywhere else, it'll meet up. Even in that sense, one cosmic sense, the electric field vectors go to infinity and wrap around and come back to the field. Okay, so those are some neat visualizations about the electric potential, and this final slide is kind of interesting just because it shows that bioelectricity is active from the human heart, and also the brain can do these sorts of similar pictures here. You can map the electric potential. I know there's a lot of magnetic effects in the brain, but you can map the electric potential surfaces of the human body from the fact that we're modeling the human heart as an electric dipole, right? Model the little electrical components in the heart create kind of a dipole shape, and we can see that picture. So that's an interesting picture. But yeah, these are the types of visualizations that we want to do. In the next chapter, we will be going through how the electric potential is connected to the electric field. Both of them are created by a source charge, so it only makes sense that they would be, it only makes sense that you would be able to connect them in some way. So that's the topic of next chapter. Until then, thanks for your time, and we'll be back here for the next chapter. Take care.